All right. Welcome, everybody. I think we're good. Okay. Looks like everything's working. So, welcome in. Welcome to the last week of the class. We're finishing up. We're almost there. So, don't give up. Finish strong. Um, so basically, you need to get your exam taken this week. So please get that taken care of. I cannot go past the end of the course. So you really need to do what you got to do to get that test taken. Um, remember that the what? That was weird. Um, remember that the practice exam is at the very bottom of the page. It's at the very bottom of the Canvas page, so you can get your practice final exam. Use the tutors, use study groups, whatever you need to do to understand those problems. Chapter 7, you are responsible for doing the Chapter 7 homework, but Chapter 7 will not be on the exam. Okay, it's just too fast. I can't expect you to be really good with it in like a couple days. So it just isn't quite reasonable. So you need to know this material. Some of you will need it for the future, and you'll need to do the homework on it, and we'll talk a bit about it. But this Chapter 7 stuff won't be on the test. Everything previous to that could be on the test, right? So everything before that you might see. We're going to start today by covering the conic sections and see what that's about. And then we'll go from there. So before I dive into the mathematics, are there any questions, concerns about how to make sure you get this class wrapped up correctly in the next few days? Okay. If there's any questions, throw them into chat. One person did send me a message about their personal situation regarding their attendance of the meeting, so thanks for that. I saw that. And then to everyone else, let's see, problem 12 and 6.2. Let's see, 6 point, oops. Let me move that real quick there. Oh, I reset everyone's late passes. Just so you have fresh late passes if you need it. Let me see. Let me go to the course. What are we looking at? 6.2 number what? 12. Okay, let's take a look at that. Okay, so I'm looking at question 12 here. Let's see. We'll go over things that hopefully will help shed some light on that. We've got your center, we've got your vertex. This is for what ellipses, and then you've got your focus. So we'll go over the bits that have to do with that. I don't know if I'll have time to go over that a specific question, but we will definitely cover a lot of that material. So hopefully that will help you be able to go through and do that. There's a question from the YouTube stream. When is the last date to turn in all chapters in to get graded for your final grade? So the due dates. So whatever the due date is, let's see, I want to make sure I don't expose any grades here. Let's see, if I go here, I should be able to go to dates. So the last homework is due on the 28th. So that's the last, basically on the, that's the last date, right? I'm not sure exactly what date I'll actually, over the weekend, that I'll actually sit down and grade everything. See, the 20th is Friday. So plan on your last day. Officially, the last day is the 28th, right? I don't know when I'm actually going to pull the grades down, whether that'll be Friday or Saturday or Sunday. I kind of have some stuff going on this weekend, but one day this weekend, I'll pull those grades down. So officially, the last day to do homework is the 28th, okay? So to answer that question, okay? Any other questions or concerns? No. Okay, then let's dive into chapter 6. And while we're at it, let me open brief introduction here. So we are covering conic sections to start off. And conic sections, let's see if I can fit this on here. Let's make this a little smaller. Oh, that's it. About like that. Okay, conic sections. So conic sections go back to the Greeks, and they mean section in the terms like biology. In biology and medicine and stuff like that, when they talk about a section, what they're talking about is a slice of something. Like you may have done this in biology class where you slice something really thin and then you put it on a slide and you put it under the microscope with a light underneath it and you can actually see through the thing. So you can see like cells and stuff like that. That's called a section. So when we talk about conic meaning cone, section meaning slice. So conic sections are slices of cones. And the Greeks were very interested in the different ways in which you could slice a cone because it turns out you come up with some different shapes. And those different shapes are actually ones that we use in society a lot. And you can see them right here. So if you take a cone and you just kind of cut parallel to the table, you just cut straight right through the cone, you get a circle right there when you slice it. If you cut at a bit of an angle, then you get an elongated, kind of a deformed circle that we call an ellipse. So it's almost like someone took a circle and stretched it in one dimension, and you get a bit of an ellipse. Now, if you increase that angle even more so that the section never actually exits, see how when you take the slice for an ellipse, your slice enters and exits the cone? But imagine this cone was infinite. It just went down forever. Here, for the parabola, if we increase that angle even more, then when we slice the cone, notice it never actually exits the cone. It just stays inside the cone. That forms a parabolic shape for us. And if we go even more, if we change that angle even more, we get what's called a hyperbola. Now, a hyperbola can be a little bit confusing for people because sometimes a hyperbola can be confused for a parabola. Like sometimes if you graph it, you'll look at it and go, oh yeah, isn't that just two parabolas? And the answer is no. A hyperbola is in fact quite different, but they can look similar to a parabola. If you don't have your screen oriented the right way, the hyperbola can sometimes be mistaken for a parabola. But we'll talk about how it's actually a very different thing. So those are the conic sections. They're very important. You're all familiar with circles. You've all seen ellipses. Parabolas have come up throughout your math classes. Hyperbolas might be new to you, but hyperbolas do come up in construction, architecture, all sorts of different stuff. Hyperbolas come up in. So they're not everywhere, but they do actually, they exist in modern society to I would say more limited than the parabola. Parabolas get used all over the place, even if you don't realize it. And circles and ellipses, you won't have to look very hard to find circles. There's probably circles in the room with you, and you're familiar with ellipses. Parabolas get used sometimes in engineering type things. Satellite dishes, if you've ever seen those like little radars people can hold. And it like collects sound. So you have like headphones on and it picks up sound from far away. Those are parabolic in nature. So a lot of things are engineered using parabolas because of the interesting effects you get when you have the waves bouncing into the parabola and they all focus on a certain point. That can be very helpful when you're using things like telescopes or radar and all sorts of stuff. So especially these top three get used a lot in society. Okay, so let's take a closer look then at that. Let's see. Let's put this back up here. Okay, so let's take a look at the parabola. And the nice thing about conics is for the most part, you're just using some formulas. So you want to know those formulas, but once you know the formulas and how they work, as long as you also know completing the square, you're probably going to be pretty good to go. Let's see. Let's get my hands on the ebook here. And let's bring that in. So you can see here's another popular way of showing those conic sections, which is to have a number of different cones. And then we're slicing them in different ways. So you can see again, circle, parabola, ellipse, hyperbola coming up. Okay. Sometimes people think the hyperbola is just two different parabolas going different directions, but as you'll see, it definitely isn't. So we'll get into that. So there's this definition of the parabola. And the conics at first are a little confusing because sometimes the way we define them is not super helpful in understanding like how to use them. They give us an important property, but sometimes we're still left kind of scratching our head going, right, but what is it really, right? So here's our definition they give us. A parabola is the set of all points x, y in a plane such that the distance of x, y from a fixed line is equal to the distance of x, y from a fixed point that is not on the line. Okay, so already that was a pretty confusing sentence, right? But we have a line, and then we have a point somewhere not on the line, and we want to find all the points that are equal distant from this line and this point, right? That's what a parabola is. That's what they're saying in that first sentence. Okay. Oops, I'm kind of off the screen for the YouTube stream. So you have your line and a point, right? I'll repeat that since I was facing the kind of a bad direction. You have your line and a point, and you have all the points that are equal distant from this line and this point. That's what a parabola is. Okay, so let me move this over so I'm facing the right direction more. The fixed line and the fixed point, which lie in the plane of a parabola, are called the directrix and the focus. So the directrix is that line, and the focus is that point. Okay. The axis of symmetry of a parabola is the line that is perpendicular to the directrix and passes through the focus of the parabola. It's the symmetry for your parabola. So don't overthink that sentence. If you were to fold your parabola in half so that the left half or one half lined up on the other half, the line that you'd get in your paper, that crease, that's the axis of symmetry. So that one's not as complicated as it sounds. The vertex of the parabola is on the axis of symmetry midway between the focus and the directrix. So that's the point right in between your that point and the line, right? So let's look at a picture and try to make sense of this stuff. Here is a picture. So we have this line right here. This dashed line is our directrix. And then we have this point right here. That's our focus. So we have this point, the focus, this line, the directrix. All the points that lie equal distance from these two things, that makes up this parabola. So this one right in the middle right here, that's the vertex. So it's right in between. It's like the most obvious point. It's halfway in between the focus and the directrix. That's our vertex. And then notice that you get this curve in both directions that are going up here. So we have this distance is equal to this distance. So that's why you get a parabolic shape. So that's one property of parabolas, but that doesn't exactly help us dive into what the parabola is or like how to manipulate it or how to find it from certain problems. So we'll look a little bit more at that. But that's the idea of what a parabola is, which I know is a little bit different than when you've seen parabolas previously and you've been graphing these things. Comes out a little sometimes it's like we just give you an equation, graph it, but you want to kind of be able to visualize, well, what's actually happening with a parabola. So they derive the parabola here. So you're used to parabolas that are they either open up or they open down. We talked about those when we talked about graphing quadratics. Well, you can also have parabolas that go sideways, left or right. Now, it's important to note that those parabolas would not be functions, right? So they're going to have certain properties that don't behave as nicely as they're used to, because the reality is most of the time when we're dealing with conics, we are dealing with something that is not a function. So not as well behaved as what we're used to. So they go through and they derive everything, and you get down to this, x squared equals 4py. That's kind of the key that you need to know here. This is what they call the standard form of the equation of an upward opening parabola with vertex at the origin is x squared equals 4py, where p is greater than 0. If p is less than 0, then it's facing the other direction. The derivations of the standard forms of the equations of parabolas with vertex at the origin but open downward to the left or to the right are similar. So you have some examples here where we've got a parabola opening up, parabola opening down, parabola opening left, parabola opening right. So we have these different forms here, but you can kind of see they all sort of carry over. You've got your directrix somewhere, right? It's either horizontal or vertical. You've got a focus, and then you've got your curve that sits in relation to that directrix and that focus. So generally, you're either going to be dealing with the form x squared equals 4py, in which case your parabola either opens up or down, or you're going to be dealing with y squared equals 4px, in which case your parabola opens left or right. So you can just kind of remember that. And remember, if your p is positive, then your parabola is going to open in the positive direction. If p is negative, then it's going to open in the negative direction. Okay, and this chart tells you like where your vertex and focus and directrix and all that kind of stuff is for your most basic parabolas that you have to deal with. Yeah, we don't need to go over those. So I think the examples, you can follow those examples pretty well. And I should have, let me double check here. What do I have? Oops, that's for the ellipse. Yeah, so I've got a video for the ellipse. I believe a video for the hyperbola. And there should be one for the parabola. Yeah, so I've got a video that I made for each of these. Parabola, I think this book in here is using this video is using the old book, but that's okay. It's the same information. It's just from a different textbook, so it's not going to match your book exactly. But it's the same problems that you're going through and doing, right? So I would encourage you to watch those 3 videos, ellipse, hyperbola, parabola. Those are going to help quite a bit. And then follow the examples in the book. So when we're looking at these, you're starting here with y equals 1/6 x squared. So what you should do then is go back up to go back up to this chart and remind yourself which are you working with, right? So in this case, it's got like the squared part is by itself. So I would take this and I would multiply both sides by 6, which would give me 6y equals x squared. And then go up and match it here, right? And go, oh, I'm dealing with the x squared equals 4py part. And then you can construct the thing from there, right? So let's see. For the sake of time, I'm going to move through this one. So like watch the video that's posted in Canvas. I just don't want to get too hung up on stuff there's already videos for and then not get to stuff that people get a little bit more confused with. So they're able to figure out that the p is 3/2. And then once you have that p, you can start plugging it in to get other information. And then you get things like right here, we're getting some points on there so you can graph it, draw your parabola through there, do all that stuff. So just kind of follow the example in that situation. And then there's just sort of working backwards. If you're given a graph, how do you go back to get the equation of the parabola? So what we just looked at, those were parabolas at the origin. Okay, so what if your parabola is not at the origin? What if your parabola is shifted horizontally or vertically? So that's what they're talking about here. Parabolas with vertex at the point HK. So we've shifted things off the center. But the good news is, look, they give you this chart again, except now they do it, it's a little bit more complicated, but they give you everything you need right here to figure out how to go through and do these. Okay, so you've got your parabolas that open up and down, your parabolas that open left and right. Notice here, the H is if you think back to the transformations that we did at the very beginning of the semester, your H here is going to be a horizontal shift, and your K here is going to be a vertical shift. So HK is where your vertex is. Notice the vertex was at the origin. Now we've shifted it horizontally and vertically, but we know how much we've shifted it, and it just moves this vertex to the new position HK. So it's very similar to what we did earlier, but now there's the H and K floating around. So sure, that makes your vertex and your focus a little bit more confusing, but just at the beginning of these problems, figure out what your H is, figure out what your P is, figure out what your K is, and then just come back to this chart and go, okay, what kind of thing am I dealing with? Is my P greater than 0? Where's my vertex? Where's my focus? You literally just plug in you can see. If you figured out early on up here in the problem what H, K, and P are, you just plug them into everything else, and you'll have all the information that you need in order to finish that problem. Okay? And then you go from there. So writing an equation standard form. So they keep having these things. They keep talking about standard form. So if you're getting confused with standard form, look in the book, look in the ebook, and look up where they talk about standard form. Now this is a thing this is what I wanted to make sure I had a little extra time for. This is probably the most confusing part for students, is when you're given something in the form that is not in standard form, then this becomes very hard, right? Notice how this chart makes things very easy for us as long as our equation is in this standard form that we're used to, right? Because you can see the H and the K and the P, and you can figure everything out in this case. But this problem down here is not written in that form. It's just written in some kind of like messy equation form. So by looking at this right here, right, as it exists right here, I can't see the H and the K and the P. I don't know what those are. So what we have to do is work to put this in the form of standard form, right? That's the easiest way to do it. Remember back in algebra when we would have like a linear equation and it was just in some chaotic form, and then we would put it in slope-intercept form, the y equals mx plus b form, and then we immediately could say, oh, I know the slope, I know the intercept, I know all the stuff I need to know about the line because we have it in the right form. Well, that's what we need to do here, except it's a much more complicated version of it. So you can see what they do here. I can kind of walk through what's happening here. To make sure everyone understands, is we're using completing the square to put it in the right form. So right now we're just in this chaotic form that is not standard form. So what do? Well, they get all the y terms on the left and all the x terms end up on the right. So you've moved x terms to the right, you've moved y terms to the left and grouped them together. Then you factor out anything you can, in this case a 3, right? And then what happens is we end up completing the square. Okay, so remember how completing the square works? We take half the coefficient on the variable, we square it, and we add it to both sides. The reason we do completing the square, it's right there in the name, is it takes something that is not a perfect square, it turns it into a perfect square, and then we can factor the thing. Okay, so that's the whole point. See how like down here, this is factored as a perfect square, and up here it's not? That's what completing the square does. It takes us from that form that doesn't work and turns it into a form that does work. So basically we've got this inside the parentheses, you do your completing the square. So what do? You look at the y variable and you see how we have a 4 there. So you take half of 4, which is 2, and you square it, which is 4. So that means we're going to add a 4 in here. Now this looks weird because you go, wait a minute, we're adding 4 on the left, but I'm adding 12 on the right. Aren't we supposed to add the same thing to both sides of the equation? And the easy thing to miss is that 4 is really being multiplied by the 3, right? It's really 4 times 3. So even though you wrote plus 4 in here, you're really adding 12 to both sides of the equation, okay? You're adding 12 to both sides. So that's like the easiest place for people to get messed up. Because your brain gets confused. You wrote plus 4 on your paper, but you really added 12 because this 3 is distributing in. It's like a leverage. This 3 is leveraging the 4. So even though you put plus 4, you really have a plus 12. Okay? So once you get past that, then you factor this and go, oh, okay, 3 times y plus 2 squared. Okay. Right? That was the whole point of completing the square, to make this a perfect square. And then on the right, you just factor this as best you can. You add the 8 and the 12 to get 20. And then you factor the 4 out, giving us 4 times x plus 5. And then where did this 4/3 come from? Well, remember we have this 3 out front, but that's not really in our form. So we divide both sides by 3, and we get this. Y plus 2 squared equals 4/3 x plus 5, which does fit this form up here. Right? Then it's in, what was it, this one? It's this form right here, right, on the right. Except for we haven't technically pulled the 4 out yet, but that part's easy. But so you can kind of see it matching, right? Right. So if you want to take 4/3 and you want to factor the 4 out to make it 4 times p, well, if you divide 4 out of 4/3, you get 1/3, right? So it's 4 times 1/3. So your p would be 1/3. So you now have all those pieces that you need. You have the p, you have the k, you have the h, and then you just go back up to that blue box that gives you the equations, and you just sort of plug everything in, right? And you'll get all those pieces that you need. Okay. So then you can see a couple applications here, like they talk about headlight design. Anytime you have light or sound being reflected, like trying to be focused in a certain way, then you are probably dealing with a parabolic shape. So the headlights on cars, parabolic in nature. A lot of times when they're dealing with acoustics for certain things, you want to project sound in a certain way, you can use parabolics to do it. So definitely useful. It's not something you just run across every day, but there are lots of people who are designing things and they use parabolas in order to manipulate sound or light in a certain way. Okay, so that is parabolas. Let's look at something that's a little bit of a step up, but not bad. If you understood everything we just did, then you're probably going to be okay with the rest of it. So the ellipse is a largely misunderstood thing, and it's because of the way we teach it. And I think the way we teach it is actually kind of silly sometimes, in some ways. But a parabola, or an ellipse I should say, is really just a deformed circle. In fact, what you could say is that a circle is a very regular ellipse. In other words, the relationship between a circle and an ellipse is the same as the relationship between a square and a rectangle. So like a square is a rectangle, right? Not every rectangle is a square, but every square is a rectangle. If you have a rectangle where your length equals your width, then you have a square. Well, that's how it works with ellipses. If you have your major and minor axes are equal to each other, then you have a circle, right? And to the point where you actually don't really even need to learn a different set of equations for circles and ellipses. You could just do everything with ellipses. If you just use the formulas that you've learned for ellipses, those will work for circles, right? They will work for you. It's just that circles are a little bit of a more simplified situation. But again, you don't really have to learn 2 different sets of formulas. You could just use ellipses always. So let's see our definition of an ellipse. This is another one that sounds confusing, and then we can make sense of it. An ellipse is the set of all points x, y in a plane such that the sum of the distances x, y from 2 fixed points in the plane is equal to a fixed positive number d, where d is greater than the distance between the fixed points. Now that sounds confusing, right? What they're saying here is, let's see if there's a, I was trying to find the best picture I could here. Basically, this picture is what we're looking at. You have 2 fixed points called the foci, and foci is just the plural for focus. So we don't say, oh, your 2 focuses, we say foci, right? The vocabulary is not a big deal. I just want to make sure you understand when you hear those words. So you've got focus 1 over here. You've got focus 2 over here. Let me make this a little bigger so we can see. You've got focus 1. You've got focus 2. Now, if you took like they do this in class sometimes, it's if you do it right, it comes out well. Imagine if you had a piece of string that was attached to the whiteboard at focus 1 and focus 2, and it was kind of loose, just hanging there. And then you took a pen and you put all the tension in the string. So you took all the slack out of the string and you just traced around. What it would form is an ellipse. It would form this shape of an ellipse. And that's because the distance of the string the total length of the string does not change, and the string is composed as the sum of the two distances. So, you can see, you pick any point on the ellipse, the distance, you take the distance from this first foci plus the difference to this second foci, that remains constant. So as you move this, those two distances are going to change to something else, but if you add up those two distances, they're going to add up to the same amount as we got over here. That's what they're saying in that definition, okay, with that sort of very wordy sentence that we just listened to. Okay, each of the fixed points is called a focus of the ellipse. Together they are called foci. So we have what's called a major and minor axes. So basically what you have is you have your longest distance across the ellipse and your shortest distance across the ellipse. The longest distance across your ellipse is called the major axes, and the shortest distance across your ellipse is called the minor axes. Okay, in a circle, the major axes and the minor axes are equal to each other. They're the same length, right? Because in a circle, no matter how you measure the distance across the circle, it should be consistent. So in a circle, it's just that the major and minor axes are equal to each other. Just like in a square, the length and width are equal to each other. Okay? It's really the same idea. So they start out again with the situation where we're centered at the origin, and then they're going to give you, they derive the stuff. We get there, we get this formula. And then they give you the nice blue chart here, which tells us how to put everything together. Okay, so notice you have your formulas here. X squared over a squared plus y squared over b squared equals 1. So basically, you can have an ellipse that's stretched horizontally, or you can have an ellipse that's stretched vertically. You can have ellipses that are stretched diagonally, or like at some kind of an angle, but the mathematics involving those is much more complicated. So some of you will see those again, probably, I think, Calc 3 and in linear algebra. You start messing with stuff like that again, but it's a huge step up computation-wise. So that's why for now we just mess with the ellipses that are stretched horizontally and the ellipses that are stretched vertically. Now, one thing, I helped a student with the homework the other day. They were confused about how to write these. What they were writing in the homework was mathematically correct, but they weren't writing in this form of a square, which is what the book is looking for. So if you're having trouble getting the homework to take your answer in the way that you like, you're looking at it going, I think this is right. I think my numbers in the denominator are correct. Instead of writing 36 down here, try writing it as 6 squared, because for at least some of the problems, that's how they want you writing that. Okay, I think that's why this student wasn't getting credit for it. Even though their equation was correct, they weren't writing it in this squared form. Now, in the real world, no one really cares if you write 36 versus 6 squared. But I think the homework is just trying to force you to understand that little piece. So keep that in mind if you're having trouble with that homework bit, okay? And then they tell you all the pieces here. So basically, once you figure out your A and your B, and then you figure out your C using this equation right here, once you have your A, B, and C, you can figure out the center, the foci, the vertices, the major axes, the minor axes, all those pieces. So if you get stuck on the foci, I think that was maybe the question that was earlier, was about foci for ellipses. They tell you here in this blue box, once you identify A and B, which is what you get from the denominators in your equation, from that you can construct C. And once you have A, B, and C, you can just plug it in and get all these other pieces. Okay? Yeah, and it looks like I probably won't have time to do that homework problem. But I think, if I remember right, that's what that homework problem was about. Okay, so if we take a look, an ellipse centered at the origin. So here we have, let's take a look at this separately. let's do this. These ones are a little easier to see. So let's say we've got 16x squared plus 25y squared equals 400. Okay, so that's an equation of an ellipse. Oops, not 26, 25. Okay, so there is our equation for an ellipse, but it's not in that form that we're used to, right? It's not in one of these forms that we're used to here. It doesn't look like this, and it doesn't look like this right here, right? Also, notice the difference. I feel like books make this way more complicated than it needs to. Notice all they're saying is that the A and the B, like in each case, one's bigger than the other. So here, A is greater than B, but they've switched them around here. Here they say A is greater than B. So they're basically, the key is to just look at the value under, is it underneath the X or is it underneath the Y, right? Because if you'll notice, the distance from the basically here, your distance from this vertex to this one, the major axes going across the whole thing, that's going to be, so you're going from negative A0 to A0. So basically, if you start at the center, you come out A in each direction horizontally. In this case, A is the one that's beneath your X. So remember, X's are horizontal. So you just look under your X, and whatever the square root of this number is, you go out from the center, A, the square root of this A squared. You go out that much, and then Y, that's always vertically. So whatever is underneath the Y, you take the B, not the B squared, but the B, and you go up and down that amount. Okay? Books make it very complicated by giving you what looks like two different formulas, but it's actually a lot easier to just think your way through it. The A and the B are giving you the distance that you move horizontally and vertically from the center. And how do you know whether to move horizontally or vertically? Well, you look at your X and a Y. X is horizontal, Y is vertical. Okay? So when we go back to our problem over here, so we've got a situation where we're looking at 16x squared plus 25y squared equals 400. But notice that we're not in the form that we're used to. So what do? You just divide everything by 400. Okay? So this becomes okay, so it's starting to look a little bit more like our equation for a circle. We're not there yet, but it's getting closer. And actually, that's the main difference between when you look at the equation for a circle and you look at the equation for an ellipse, it's easy to go, he said they're the same, but they don't seem like they're the same. That's because for a circle, if you divide both sides by the right side, you end up with a 1 on the right, and it's going to look just like your ellipse formula. Right? But for some reason, we like to write those two things in different ways. It's kind of silly, actually. And then in this case, so now we're going to simplify things a bit. Oops. And we're going to get x squared over 25 plus the fraction y squared over 16 equals 1. Now all of a sudden it looks like it's supposed to. Okay. Now let's see how we would go and graph that thing. So remember, this is an ellipse centered at the origin. So let's go over to our graph. I highly encourage you to use Desmos in these sections. Like, use Desmos. It's helpful. Right? If you're having trouble with one of these homework problems, use Desmos, graph the thing. See if you can use that graphing utility in order to help you work through the problem. So we've got our center is at the origin. Okay, so we've got our center. And then if we're looking at this, this tells me that horizontally, because under my X, that's horizontal, this tells me I want to move 5 units. So that means I'm going to go over 5 this way and over 5 this way. So that's going to be 5, 0, negative 5. Oops, that's not right. Negative 5, 0. Okay, these 2 points. So I'm saying my ellipse should go through those 2 points. Okay, what about vertically? Excuse me, I'm going to need to get a water in a second. What about vertically? Well, y tells us about vertical. So if we take the square root of 16, we get 4. That tells us we're going to move up and down 4 units here. So that should give us 0, 4, 0, comma, negative 4. So we've got those points. So when I graph this, it should go through correctly. So let's see, 16x squared plus y squared, plus 25y squared equals 400. Sure enough, it went right through all those points that we said. Okay, now here's something that can be helpful. See how I graphed it in the original form we started with the problem? Well, here's a thing that you can use to easily see if your work came out right. Because how do we know I didn't make a mistake along the way when I was doing this work? Maybe I made a mistake in here. How do I know? Graph both versions. So we've got the 16x squared plus 25y squared equals 400 that we started with. Now what if I do x squared over 25 plus y squared divided by 16 equals 1. Notice how it's the same graph? Oh, well then I know my algebra's good. Right? What if I had done this? Notice how that doesn't look right anymore? Or if we had something like this? Oh, somehow I deleted it. Can I control Z out of it? Oh, I can control Z out of it. Okay. So if I do something like this, notice how they don't fit right anymore? That tells me that my beginning point and my end point aren't actually the same. So you can always go through and write it in the write the beginning form that the problem was given in, write the form that you ended up with, and just see if they match. If they match, then you should be good. Okay. So with writing the equation of the ellipse, you're really just working your way backwards. So what we did was what we did is you work your way to this form, and then you start pulling out your A and your B and your H and your K and all that kind of stuff. Except they're giving you the H and the K, and then you're figuring it all out from there. So let's take a look here. Let me finish my thought, and then we'll take a look. Right, we got all that. Okay, so here they have a problem finding the equation of an ellipse. That seems to be a thing that some people are getting confused on. So writing that equation. So let's go over that in just a second, but I want to double check that there's not. All right, this is what I wanted to go over first. And then we can kind of work through some of those things. Equation of an ellipse with center at the point HK. So this is the same thing we do. They introduce conics as being centered at the origin. And once you're comfortable with that for the easier problems, then they shift those things horizontally and vertically. So that's what we're dealing with here. But it's the same old thing you're used to. X minus H, that gives you the amount of horizontal shift. Y minus K, that gives you the amount of vertical shift, right? X is horizontal, Y is vertical. So now they give you these, and these are starting to look a little cramped, like there's a lot going on in there, but it's not as bad as it looks. As long as you go through, figure out what your H is, and write these down separately on the side of your paper. Write H equals, H equals 2, K equals -3, A equals 2, B equals 5. Like write all those values down and then figure out what C is, right? I see students trying to keep track of all this stuff, but like they don't write anything down. Well, how are you going to do that? If you have an H, a K, an A, a B, and a C, that's 5 different values and you're trying to like remember them all. That doesn't make any sense. So write down your H, your K, your A, and your B. Figure out what your C is using this. And then you can just use this to go through and plug everything in. Okay, then like once you have your H and K written down, you go, okay, here's my center. I can use that to get my vertices. I can use it to get the major and minor axes. And once you have all those pieces put together, then the problem, although it looks very confusing, if you're just doing it bit by bit on your paper, it's much easier to work through those kinds of problems. Okay. And so it's really the same problem here, except they're using it's shifted at this point. And then we have the old completing the square. So you can see kind of a pattern how these work. They introduce the formulas at the origin, then they introduce the formulas for HK, then they have you do completing the square. So like once you get that pattern and it clicks for you, then you're kind of just doing the same thing but with slightly different formulas. So you can see right here what they're doing is also completing the square. So we're given this. Let me make that bigger. We're given this, which is the equation of an ellipse, but it is not the equation in the form that we're used to. By looking at this, I don't know what H is. I don't know what K is. I don't know what A, B, and C are. We don't know any of those. So we want to get things in the right form so that then we can identify those values. So basically what they do next is they get all the X terms in front. Then they get all the Y terms next. And then you just do completing the square on each one, right? So completing the square says you take half the coefficient and square it. So half of 6 is 3. 3 squared is 9. Notice we're adding a 9 in here. Over here, half of 2 is 1. 1 squared is 1. Notice we're adding a 1 in here. And this is where, again, you have to be careful because your brain and your hand will disagree. Your hand is saying, no, I wrote plus 9 and I wrote plus 1. But your brain is saying, no, you wrote plus 9, but it's being multiplied by this 5 over here. So you really added 45. So then you have to add 45 on the right. Over here, we added plus 1, but it's really being multiplied by 25. So to balance it, we have to add 25. That's the easiest place to mess up in this problem, assuming you know how to do completing the square. And then after that, you divide both sides by 50, things simplify down, and sure enough, here you now have your problem in standard form. So here's your H is 3, and your K is, be careful here, think for a second, what is K? K is -1, right? Because you might go, no, it's 1. But remember up in our formula, it has to be written as Y minus K. So if we were to write this as Y minus, it would be Y minus -1. So we have to remember that the sign is wrong here, right? I mean, the sign's right for this equation, the way it's written, but when you're trying to determine what K is, it has to be written as Y minus -1, making K -1. Otherwise, you're going to end up on the wrong side of the graph, okay? Your A squared is 10, your B squared is 2, so you know, in this case, your numbers don't come out quite as convenient as when they're perfect squares, but that's okay. They don't have to come out perfectly. So you've got your A and your B. Once you have your A and your B, you can figure out what your C is, and then you just plug everything together and get your ellipse, like they do right here. Okay? So it takes a little bit of work, but it's mostly about being organized, identifying the H and the K and those different pieces. Ellipses also come up a lot in space. Okay, what you have to realize is in space there's essentially no circles. Everything is in at least is some way a little bit of an ellipse, and that actually held up astronomy for a long time because for various different influences that were not really helping astronomy but were powerful at the time. You know, there was this thought that things in space had to be perfect because they were made perfect and blah, 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 all this stuff. So they thought that the orbits of planets must be circles. And what they found was they were not able to reliably make predictions. They could make predictions a couple days out about where should Jupiter be in the sky in a couple days, where should Mars be in the sky in a couple days. But if you tried to make predictions like 3 years out, it wasn't working. And they finally figured it out. That's because they were assuming that everything moved in circles, when in fact, things in space don't move in circles, they move in ellipses. So that's why they talk about the elliptical orbit of Halley's Comet. Every single one of the planets orbits in an ellipse. In fact, the sun sits at one of the foci for that ellipse. So we talked about the foci, like why are those important? Well, that's where the sun is for the planets that orbit around the sun. Okay. Now, the closer you get in, so you look at like Mercury and Venus, they have orbits that are very close to being circular, but they're not quite circular. They're a little bit elliptical. And the further you move out and you start getting to like Saturn and stuff, those orbits are very obviously elliptical, right? At least obvious to us now, because we have much better ways of measuring these things. So that's another important place that these come up. Okay, let's go back to that problem because it looks like 2 people now have had a question about it. So let's kind of work through this one and hopefully we can help people with that problem because it seems like people are having an issue with this. So finding the equation of an ellipse, right? I believe that's the question that's being asked. So determine the equation in standard form of an ellipse with center at the origin. Okay, that's nice. So making it at the origin makes it a lot easier because our h is 0 and our k is 0 right out of the gate. So that means we can use those earlier formulas that use being centered at the origin. So that's helpful. One focus is at 0, -3/2, and one vertex at 0, -2. Sketch the ellipse. Okay, so let's go ahead and sketch this using our Desmos here. Let's get rid of all this stuff. Okay, so I haven't done this problem today, so you'll have to stick with me if it takes me a second or two to remember exactly how I want to do these steps. But here's how I would approach this problem. Okay, we have one focus at 0, 3/2. So that's one focus. And we have a vertex at 0, 2. Okay, sketch the ellipse. So if we go back to our picture here, if we go back to our, let's see, so I can switch back quickly. That's on page 513. Okay. Oops. Where's my formula? Okay. So if we look at our formula, right? So I would look at these, and you kind of can see the orientation. So for this kind of an ellipse, you have what? You have vertex, focus, center, focus, vertex, all oriented horizontally from each other. And over here, we have vertex, focus, center, focus, vertex, oriented vertically from each other. So it seems to me like this is the kind of one that we're dealing with for our problem, because the foci and the vertex seem to be vertically oriented. So, and we know we're dealing with one at the origin, so we're really dealing with this kind of an equation right here. This is what we're looking at. In fact, I should have put the center in here because I believe ours said we're centered at the origin, right? So let's get that look in there. So since these are on the same side as as each other compared to the vertex, in other words, they're not down here, then it looks like we could just reflect these downwards. So we should really just get the opposite scenario when we do that. So we should be able to say that the other vertex is going to be at 0, -2. And the other, nope, so that would be the, yep, that's right. And then the other foci will be at 0, -3/2, like that. And let's go ahead and color these. Let's keep the, let's make the foci orange. And we will make the vertices blue. so that we can tell the difference between them. See, now they're kind of matching up. We see we've got vertex, vertex, foci, foci. We've got our origin in the middle. Okay? So then I would start to figure out, like, okay, so from here, what can I figure out from that? Well, we have this distance here. Let me make sure I'm not doing this in a more complicated way, because I don't want to do it harder than it needs to be and confuse everybody. So let me just double check. Yeah, okay, good. That's what I was going to do. Great. I just didn't want to overthink the problem. So basically what we can do is we use this graph that we've got up here to start to make sense of some of our pieces. So if we go back up to our chart, we know, okay, this vertex, the distance from the vertex to the center, that's going to be the square root of the denominator that's under the y term, right? It's going to be this thing right here. So a squared is the denominator. A is the distance given right here. Well, that distance for us is 2. So that means that we can identify that a is equal to 2 for this particular problem. So I would write that down. I don't really have room to show it on the screen right now, but I would write a equals 2 on my paper if I was doing this problem. Okay. Now we don't know how wide out here it is yet. So let's see. What are we going to do about that one? Let's see. So then, we know right. Okay, so we also know the distance from the foci to the center. So that is 3/2, right? Well, that foci is that distance c. So we basically know that we've got this equation. Well, we know what a is. A is 2. And we know what c is. C is 3/2. So by solving that equation for b, we can get b. Okay? A is given to us the distance from the vertex to the center. C is the distance from the focus to the center. And by plugging those values in, we solve for b. And at that point, you know a and b, you know the whole equation. Okay. Okay. Let's see. So there's a question here. So the way that I test on conics is I usually don't get too bogged down in the foci. So what I ask you on the test doesn't ask you for the foci. Basically, you just need to be able to do the basic graphing. So you need to be able to do the completing the square type problems that we've done, and those don't really involve, those aren't the more in-depth, really difficult formulas. So like if you're just planning to sit down and memorize all these formulas, once you get into the foci, sure, it gets a little bit confusing. But if you notice the kind of problem that I asked on here, let's take a look. And I'm responding to a student who's asking about the formula sheet. So let's look on here. If we look at the, where's the conic problem on here? So if you look at this, I'm basically asking you to graph the problem. That I think is fair. Okay, if I was really having you get knee deep or waist deep and foci and all that kind of stuff, then I could see the argument for a formula sheet. But something like this, you should just be able to understand what that's going to look like. You should be able to identify, oh, that looks like an ellipse, and then basically know your HK and your A's and B's. So like don't try to memorize this, like every step of this. Just try to understand how the basic formula for an ellipse works, right? So I'm not gonna ask you questions that involve foci. And that's like half the complication right there. Once you involve foci, things get very, very confusing. And I'm not going to have you do one of these ones where I give you, like we just worked through, where I give you a picture or part of information and then have you come up with the equation. I'm not having you do that. I'm having you graph the ellipse or the parabola or the hyperbola, probably an ellipse. It's generally an ellipse that I put on the test. Hyperbolas are a little too weird. Parabolas are a little too easy. So the ellipse makes a nice right level for a test problem. So I think this is fair to be able to graph without the without a big formula sheet. Okay. Right. Yeah. Okay. Yeah, I see no point on test Scully going over complicated. I just want to make sure, do you get the basics of how this works? And then we go from there. Okay, so, and I think that's ellipses then. I think we've done, and I think that actually takes care of the two questions that people had about that problem. So the last one is the hyperbola. The hyperbola is one that you probably will just see less in general. You probably have seen it in architecture without realizing that you were looking at a hyperbola. There are times where it shows up. You've probably been in rooms where there were hyperbolas without realizing it. For instance, they don't have a good picture of it here. But if you ever have like a lamp in your house, kind of an old style lamp, like, you know, with like a lamp shade on it. If you ever have a lamp that's near the wall, or you go to like, you know, say an older house where there's lamps, a lot of times people don't have lamps around as much anymore because you have other ways of lighting. But so just say you have a lamp that's sitting on like a coffee table or something like that, and it's got like a traditional style lampshade on top. If you look at the shape that the light makes on the wall, that's actually a hyperbola. Okay. And there's, like I say, there's other places it gets used frequently in construction, all sorts of stuff. Oops, I brought up the wrong ebook. Let me change this. Now, at first, like there's some good news and bad news when it comes to the hyperbola. One is that the formula will look very similar to you, but there's actually some big differences. So it's, like I say, it's kind of mixed. Now, this is what I mean when people first see this, they kind of go, "Oh, isn't that just two parabolas that go the other way?" But it's not. A parabola always has a curvature to it, more like a U. Whereas if you notice here, the sides are kind of flattening out, and if you zoom out far enough, it starts to look more like a V. If you pull yourself out, zoom out from a parabola, it's never going to look like a V. But if you pull yourself out from a hyperbola, they will start to look like a V. So that is one way to convince yourself that there really is a difference between hyperbolas and parabolas. In fact, let's look at one. So this is an ellipse, okay, centered at the origin. That's all fine, okay. Now, to make it a hyperbola, all you do is you change this plus in the middle to a minus. Now it's a hyperbola. And even looking at these, you know, you could be forgiven for going like, those kind of seem like really wide parabolas. But notice what happens as we zoom out. Look how straight those lines get. Parabolas don't do that. They don't, like, this looks like two V's, doesn't look like a U, right? A parabola looks more like a U. So although it's subtle, especially when you're zoomed in, they are not parabolic in shape. They are different. So with that said, remember all I did was change this plus from an ellipse to a minus. Let's look at the definition. Definition of a hyperbola says that a hyperbola is the set of, The hyperbola is the set of all points x, y in a plane such that the absolute value of the difference, that's like the one word that's changed between ellipse and hyperbola, is before we talked about the sum of the two distances. Now we're talking about the difference of the two distances, right? Is the absolute value of the difference of the distances of x, y from two fixed points in the plane is equal to a fixed positive number d, where d is less than the distance between the two fixed points. Okay, so here's the difference. Here, instead of adding these two distances together, we're subtracting them, and that gives us a different shape. It gives us the hyperbola. Okay, so this one, I'm not going to give you a hyperbola on the test. I always feel that's a bit overkill, but you will obviously have homework problems. Again, they give you the blue chart to help you work your way through it. And look at that equation, looks awfully similar, right? The only difference is if you take an ellipse and you change the plus to a minus, you now have a hyperbola. Okay, so again, you can have hyperbolas that open sideways. You can have hyperbolas that open up and down. All right. And again, you can look at the A value underneath the X is going to tell you about a horizontal measurement. The B value underneath the Y, that's going to tell you about a vertical measurement. You get your C the same way. They give you a formula for your C down here. You get that once you have the A, B, and C, you can just fill everything in. Now, what's this? These asymptotes, the line y equals b over ax and y equals negative b over ax. Those asymptotes are coming through here. It's see how these lines are straightening out? It's the lines that go through here. Here, let's see. We got y equals, what's it going to be? 4 over 8x. No, 8 over 2x. There we go. And y equals negative 2x. So I got these by taking the ratio of the a and b values, and look how they're asymptotes for that hyperbola right there. That hyperbola is approaching those lines but never quite touching them. That's why when you zoom out of a hyperbola, it looks more like a V shape, because the ends are getting straighter and straighter. They're approaching an asymptote. A parabola doesn't approach an asymptote in that same way. So you can see they're just getting straighter and straighter. So that's the equations for those asymptotes. You use, in fact, your A and B values to get the equations of your asymptotes over here. And you could see it took me twice, because at first, because I'm trying to do this while I'm talking, at first I did it the other way. I did it as 4 over 8. And then I go, nope, that didn't work. So then I made it 8 over 4, which is 2. And you can see those asymptotes worked. So even if you get confused about, like, wait, which one's the right asymptote? Just try it one way and see if it works. And if it doesn't, try it the other way. It takes, especially with Desmos, it takes a second to do something like that. Okay, so then that's kind of the big difference with hyperbolas, is now you have these asymptotes to deal with. Other than that, it works roughly the same way for how everything works. So you end up with something like this. It's not in the right form, so you divide by 144. You get this, and then they want to know what's the equations of the asymptotes and the vertices and the foci. Well, you get it in this form right here. You identify your A and your B. So our A and B are going to be 3 and 4. Once you have 3 and 4, you can figure out that C is going to be 5, right, using this right here. So you get your A and B, then you figure out C, and then you just plug it in. Here's my center, here's my vertices. Here's the asymptotes. Here's that transverse axis. The transverse axis is just a line that goes through your hyperbola. Like, it's sort of, you could think of it as being like the symmetry, the line of symmetry, so that this thing will line up on top of this thing. Okay. Oh, thanks for roll. I might actually skip roll today. We're in the last week. I'm not going to drop anybody. And if you're around at this point, I assume you're going to actually take the exam. So thanks for letting me know. I appreciate reminding me about the roll, but I probably won't get to it today because I think we'll run out of time. But I appreciate it. And then you can see once you have your A is 3, your B is 4, your C is 5, it's just plugging things in, getting your different values. You can see those numbers showing up again and again, right? 3, -5, -3, -5, 3, 4, right? These values popping up. So it's really just pin down your A, B, and C and then go from there. Finding the equation of a hyperbola. I won't give you a problem like that on the test, but it can be helpful. And then, of course, they now shift everything again, where you have an H and a K. So you have a horizontal shift, you have a vertical shift, and that does make it a little bit more complicated. But again, what you're going to do is get down here. You're going to identify your A, B, your C, your H, and your K. And once you get those 5 values, it's just a matter of plugging things into all these pieces in order to get what you end up with. Okay, so that actually ended nicely. So I think some of you, if you were so motivated, you could go ahead and I'm going to cover chapter 7 on Thursday. Some of you could work through this and start making sense of it. I'm going to talk about it on Thursday. Remember, chapter 7 is not on the exam, but you do have homework on it, so it will affect your homework grade. So if you wanted to get started on that, you probably could. I have had some students asking me for help, like emailing me with a question. I have a question on the homework. I can definitely help you on the homework. I did reset everybody's late passes, so that should be enough to get everyone through, hopefully, get everyone through to get their homework grade up where they need to get. I just reset them this morning again, so lots of late passes for everybody if you need them. Yeah, I'm gonna skip taking roll today. So I think that's about it. Do not forget to take your test. If you don't get in and take the exam, we have a big problem concerning your grade. We'll probably be coming in complete or an F, one of those two, depending on the circumstances. So please make sure that you get your test taken and that you get in there and get that squared away. I'm not adding any more Canvas assignments. I feel like people are probably busy enough just trying to finish things out. And at this point, I think people probably have their stuff squared away as far as how they're going to study and stuff. So I know I had mentioned at one point adding another Canvas assignment, but I think we just moved so fast in the summer. I just, no point in giving you any more work that you need to work through. Okay. So I think we'll end there. I'll shut down the YouTube stream. Anyone who wants to talk to me, come meet me in Zoom, and I can answer any questions that you like. Okay, thanks, everybody. I'll see you in a couple days. Yeah, okay.